Hello, my name is Nigel, and this is my R2R digital to analog converter. The digital to analog converter is a device that takes digital inputs, either 9 volts or ground in this scenario, and turns it into analog outputs, so anything between 9 volts and 0 volts.
So this is our digital to analog circuit. In this example, we only have 4 switches, but that's all right. So we have our most significant bit over here and our least significant bit over here. This might actually sound super familiar, and that's because it is, because it actually takes a lot of factors from binary, where you got 1, 2, 4, 8, least significant to most significant, or 2 to the power of 0, 2 to the power of 1, so on. You get the point. In our circuit, so the digital to analog converter, it's actually fractions of the voltage. So you've got a half, a quarter, an eighth, and a 16th. And that will slowly add. So your first one is very similar, right? You're going to add half your voltage, then a quarter of your voltage, and you can get really precise with this. This is going to look like 4.5, 2.25, 1.125, 0.5625, all the way to 0.035. So you can get pretty precise with this.
So let's flip some switches and see this in action. In this case, it should be 4.5. So it's 4.6, but that's because I replaced the batteries very recently, so the batteries are just a little higher than 9 volts. But as we go along, you'll see that the voltage isn't exactly correct. It's just a little bit lower than it usually should be, and that's just because that the voltmeter is being powered by this circuit, so it also needs some voltage. So the voltage isn't going to be exact, it's actually going to end up around 8.5, which is pretty close to where we want it to be. All right, so this is the same circuit we had earlier, right? And we are going to calculate it using Thevenin and superposition theory. So the first thing we're going to do is we're actually going to set all of the outputs to ground. So 1, 2, 3, 4. You're all ground now, right? And this is going to allow us to better calculate the circuit because we know that 2R over 2R is equal to R, which means that this 2R here and this 2R here can actually be canceled out and replaced with R. And 2 R resistors in series are just going to mean they're another 2 R resistor, just like the one up here. So we can actually do the same thing again. Now we get this. Again, these 2 R resistors are in series. So we can do it again. 2 R resistors in series again. And that actually just leaves us the output resistance is always going to equal R, which is super helpful for calculating the circuit. Because when we move on to calculating voltage here, so this is our least significant bit. This is just the least significant bit here. We've got our voltage here, our ground here, 2R and another 2R. And what we know is that the voltage here is used up between both these two resistors. And because these two resistors are equal, we know that this one takes the first half of the load, and this one takes the second half. So basically what happens is at this point in the middle here, it's V over 2. Half the voltage is still remaining because this one's taking up the first half and this one's going to take up the second half. So what we can do is we can actually apply this right here. So if we know that this is V over 2, then this here, because we've got 2R here, 2R here, this is V over 4. This is V over 8. And this is V over 16. That is the basic pattern of the R2R digital to analog converter. Hopefully this video simplified your understanding of the device. Thank you for your time.